Welcome back, everybody. So we're continuing our journey through the comparison tests. Last time we talked about the direct comparison test, or as I sometimes call it, the baby comparison test. There's a funny story behind that if you remember from the last video. So now we're going to talk about the limit comparison test. Right? So this is, maybe you think of this as the grown-up version of the comparison test. So suppose that you have two sequences and they're both positive. Remember, we'll need them to be positive, but we don't necessarily know which one's bigger than the other one. We don't have to try to get an inequality between the two. What we do is we test them by making a fraction. It's like we use this fraction as scales. Okay? Just think about the Tower of Power. If you have a fraction and you take the limit as k goes off to infinity, and well, it says there on the screen if this limit isn't 0 or infinity. Before we finish with the test, let's think about what would happen if this were 0 or infinity. So if that limit turned out to be 0, why would that happen, right? How do you get 0? Well, if you think about the Tower of Power, it's because the more powerful thing is on the bottom, right? If you get 0 from a fraction like this, then it's because the bottom is the bigger one, right? On the other hand, if we got infinity, it's because the top is the bigger one, right? So what we're checking for here is to see whether these two things tie. In other words, if this limit exists and it's not 0 and not infinity, it turns out to be a number like 7 or 15 or 3 or something, then it means that the AK and the BK powers tie, okay? That's what we're really testing for. We're weighing these series against each other, and if this limit of the fraction that we've made isn't 0, which would mean the bottom's bigger, isn't infinity, which means the top's bigger, it means they tie. And that means that the series have to do the same thing. They either both converge or they both diverge. That's really cool. It means that we can take a series that we don't know anything about, some wild, dangerous series that we have to analyze. We bring it in and we put it in our scales, make this fraction, and compare it to a nice tame series that we understand. And if they both have the same power, right? If that fraction doesn't converge to 0 or infinity, but converges to just some number, it means they tie on the Tower of Power. They're equally as powerful. So they'll both, when I make them into series, either converge or diverge. Right, so let's go back to that example we had at the end of the last video. 1 over square root of k plus 3. Well, if we just erased the plus 3, right, then and tried to use the direct comparison test, the inequality would go the wrong way to do the direct comparison test. But I mean, the truth is, how much difference does that plus 3 make anyway, right? If I plug in bigger and bigger numbers, right, into this thing for k, like when k is up to like 15 billion, square root of 15 billion and square root of 15 billion plus 3, I mean, it's not really any difference, right? This thing looks just like a square root of k. That plus 3 doesn't make any difference. And that's exactly the way we would think about it when we were doing the Tower of Power. Right? If I looked at just the sequence, in other words, I put my thumb over the sum as though I were trying to do the divergence test, and I ignore the sum and I just look at the sequence. Right? Well, obviously this sequence is going to converge to 0 because I got a 1 in the top and a square root of k in the bottom. The plus 3 doesn't make any difference to whether the sequence converges to 0 or not. Of course, the sequence converges to 0, so I can't use the divergence test, right? This is that case that we harped on in the divergence test video. The sequence is converging to 0, which means that I can't use the divergence test at all. I'm going to need something else, and something else I'm about to use is the limit comparison test, because by thinking about the divergence test and looking at this, I see the square root and I go, oh, it looks like a square root. Let's compare it to 1 over square root of k. So I have the series that I don't know, 1 over square root of k plus 3, and I have a series I do know, 1 over square root of k. Now, how do I know what 1 over square root of k does? Well, it's because I've memorized all those examples we used in the other videos, right? We know that the series 1 over square root of k, that's 1 over k to the 1/2 power. If I did a little algebra, that's a p-series, where the p is equal to a half. Awesome. So I know what the 1 over square root of k does. It's going to diverge because it's a p-series with p equal to a half. Now, how do I do this. Oh, this is an awful looking fraction, right? I had a compound fraction is the word that we would have used in like algebra 1 in high school or something. It's a fraction over a fraction. Yuck. Well, okay, I just flip it and multiply. So that's not so bad. So now my blue square root of k ends up in the top, and the red square root of k plus 3 ends up in the bottom. And now it's obvious how the limit goes because I got a square root in the top, a square root in the bottom. Those both tie on the tower of power, and so the limit's just going to be 1. So great. That means that the two series, the blue 1 over k to the 1/2 power that I knew diverges, right? And the one I'm trying to test, 1 over the sum of 1 over square root of k plus 3, they do the same thing. Right? And of course, the thing that 1 over square root of k does is diverge. So that means the one I didn't know diverges by the limit comparison test. Okay, so again, if you were to write up a problem like this, and you will, for the homework or for the exam, this is the sort of thing that I want to see. I want to see the name of the test and whether the series actually converges or diverges. And then I want you to do all the work. And so all of this, right, is the work necessary to see that. I have to set up my limit, see what the limit's going to be, and then now I know that the two series I'm testing do the same thing. What's the thing that the test sequence series does, right? The one that I'm testing against does. It diverges, so I knew the original diverged using the limit comparison test. Okay. Let's look at another example. I think we did this one also in the last video because we could just get rid of that -5 and see what happens. Well, here, if I just ignore the -5 for a minute, we can see that that looks like a geometric series. Again, the -5 shouldn't matter much. And maybe if it was a -5 or it was a +5, might make the inequality go the wrong way if we try to use the direct comparison test. Here, it doesn't matter. I'm just going to take this 3 over 4 to the k minus 5, this series that I don't know what it does, and compare it to what it looks like, which is a geometric series, 3 times 1/4 to the k. Okay? And so, I'll have to do a little algebra. I'll flip this. The cool thing is those 3's will cancel, right? And the blue 4 to the k ends up in the top. The red 4 to the k minus 5 ends up in the denominator. Now, once we've done that, how do we see what this limit's going to be? Well, I've got a 4 to the k over a 4 to the k. The -5 doesn't make much difference, so they tie on the tower of power. So this turns out to be 1. That means that my two series do the same thing. And what's the thing that my blue series does? Well, it's a geometric series. Again, remember, we've got to know all of those examples from before. Otherwise, we won't have any idea what to do when we get to this step. It's a geometric series. The r is equal to 1/4. And again, the rule is the absolute value of r has to be less than less than 1 in order for it to converge. So because my r is 1/4 and 1/4 is less than 1, this geometric series converges. So the series I didn't know what it did a few minutes ago, now I know it converges by the limit comparison test. Okay, here's another one. This is maybe more common than what we you'd see on a test. At least it's one that we didn't have in something similar to it in the last video. This is much more complicated looking, but it's still pretty easy to figure out because we just ask ourselves, what does it look like? Right? In fact, what I would do if I were doing this on a test is I'd try the divergence test first. And I mentioned that an example or so ago. If I put my thumb over the sum and just look at the sequence, let's just check and make sure that this thing goes to 0. Does the sequence go to 0? Well, yeah, because in the denominator I've got a k to the 4th, in the numerator I've got a k cubed. Okay? So the denominator wins, the k to the 4th beats the k cubed. So that means that this sequence, right, will go to 0, which means that the divergence test is absolutely, completely, and totally useless for doing this problem. It will not give us the right answer. Well, it wasn't completely useless. It made us think the right thoughts because it made us look at this and go, okay, what matters in the top? The k cubed. What matters in the bottom? The k to the 4th. So if I think about that for a second, this is This is like having a k cubed over a k to the fourth. I mean, that negative 5 doesn't really matter much in the grand scheme of things. That plus 3k doesn't matter much in the grand scheme of things. It looks like a k cubed over a k to the fourth. Well, okay, great. Could I just cancel that then and say it looks like, 1 over k? Because k cubed over k to the fourth, you could cancel, and there's one extra power in the denominator. So yeah, I mean that's what it really looks like, is a k cubed over k to the fourth, which again, if you cancel, does look like 1 over k. So let's compare it to 1 over k. That's how we know what to compare this series with to do the limit comparison test. And as we'll see as we go further along and learn more tests, the limit comparison test is exactly the right test to use with something like this. So how do I handle that? Well, I've got a fraction over a fraction. I'll need to flip it and multiply. But notice what happens now. I can distribute this k through the top here. So instead of having 2k cubed plus 3k, when I distribute the k through, I'll have 2k to the fourth plus 3k squared. Of course, the 3k squared doesn't matter. It's this 2k to the fourth over 3k to the fourth. Those now tie on the tower of power, and so the limit will turn out to be 2/3. Again, the coefficient, the 2 in front of the k to the fourth is in the numerator, and the 3 that's in front of the k to the fourth in the denominator. So we get 2/3. Well, 2/3 isn't 0. 2/3 isn't infinity. It's just a regular old number. It doesn't have to be 1 like the last couple examples we saw, right? It just has to not be 0 and not be infinity. That means that these two sequences we're testing, right, are equally powerful, right? So these series, right, will do the same thing. And the thing that 1 over k, that series does, is diverge. It's harmonic series. P series with p equal to 1. So the series that we, until a few minutes ago, didn't know what to do, okay, that one has to diverge by the limit comparison test. Okay, here's another that's along the same lines, right? We've got k's raised to powers in the numerator and the denominator. So what happens here? Well, again, if I were on a test, I would try to think through like the divergence test. The divergence test doesn't help, but it makes me ask the right questions, because what's happening in the numerator is a square root of k. What's happening in the denominator is a k squared. The k squared wins, so this sequence, right, the sequence part will go to 0. So the series, the whole thing, well, I don't know yet because the divergence test doesn't help. But it did make me look at this and go, oh, there's a square root and a k squared. So this thing looks a lot like a square root of k over a k squared. Okay, so what would that be if I did a little algebra? Square root of k over k squared. The square root of k is k to the 1/2. So if I do some canceling, I have to maybe think of the k squared as k to the 4/2, and then subtract the 1/2, because it would be a negative exponent when I move it down. And the net effect of all that is to give us k to the 3/2 in the denominator. Okay, and so that's a p series. I know what that guy does. It diverges. So if I could show that this 1 over k to the 3/2 ties on the tower of power with the series I started with, then perfect, we're done. The limit comparison test would tell us the answer. So let's do it. Let's take the series we started with and divide by this series that we think it looks like, the 1 over k to the 3/2, right? Well, okay, if I have to flip this to a little algebra, right? What happens? Well, how's this going to work? It's just the first thing I said in reverse. K to the 3/2 now, if I distribute this through, I would get 3 square root of k times k to the 3/2. So this is the 1/2 power, 3/2 power makes 4/2 power. So this 3 square root of k, when I distribute the k to the 3/2 through, becomes 3k squared. Right? And the other part of the 1 times k to the 3/2 doesn't matter much when I look at the tower of power. Neither does the 3k. I'll end up with a 3k squared over a k squared. Those tie on the tower of power, and my limit turns out to be 3. So perfect. 3 isn't 0. 3 isn't infinity. It means these two things actually, honest to goodness, do tie. So that means the series, right? Well, both series do the same thing, right? The one that I didn't know anything about and the one that I do know something about do the same thing. And the one that I do know something about, 1 over k to the 3 halves, what does it do? Well, that's a p-series. 3 halves is bigger than 1, so that means that my p-series converges. So the original series I started with has to converge by the limit comparison test.